Welcome to Visual Algebra Lecture 5.10, Normalizers of p-subgroups. The remainder of this chapter is devoted to the celebrated Sylow theorems. These describe the structure of a finite group's subgroups of prime power order, which are called p-subgroups. These theorems will allow us to prove a number of results about the structure of finite groups, including some that appear to be very unrelated. The proofs of these theorems involve clever group actions on sets of cosets and subgroups, and then the application of the theory that we've developed, such as the orbit stabilizer theorem. We will also need to prove several results about the normalizers of p-subgroups, and that is what we will do in this video. You can think of this lecture as the prerequisites for the exciting Sylow theorems. So let's dive in. Let's start with a fundamental result known as Cauchy's theorem. This says if P is a prime dividing the order of a group G, then G has an element and hence a subgroup of order P. In particular, if the order of the group is even, then there's an element of order 2. This is something that, if you're like me, you never really thought about. You just sort of assumed that there was one, but it has to be proven. And the proof requires, as far as I know, a very unusual application of a group action. So let's see how it goes. Let capital P be the set of ordered p-tuples of elements from G whose product is the identity. Observe that we can choose the first p minus 1 elements freely, and then xp is forced. It has to be the inverse of the product of x1 up to xp minus 1. In other words, the number of such p-tuples is the size or order of G to the p minus 1. Now we're going to define a group action on the set that you probably won't see coming. So the group ZP or CP if you prefer, the cyclic group acts on P by cyclic shift. So phi is a homomorphism from ZP to the permutations of P, and let's take a p-tuple, and when we press the 1 button, apply phi of 1 to it, we get x2 all the way up to xp, comma, x1. Okay, so this set of p-tuples is partitioned into orbits, and each one has to have size 1 or size p because it has to divide the order of the group acting on it. So here's kind of what it looks like up here. So we have like x1, comma, xp, and then we apply, we press the 1 button and we get x2, comma, xp, comma, x1, and then we do this again and we get x3, comma, all the way up to xp, x1, x2. And so we get these orbits of size p, and then we also get orbits of size 1, potentially. And let's think about what an orbit of size 1 is. So an orbit of size 1 is of the form x. Well, so it's a p-tuple that when you cyclically shift it, you get the same thing. So that means all of these entries have to be the same. So it's of the form x, comma, x, up to x. So that's an orbit of size 1, but it has to have the property that x to the p equals the identity. So if we're looking for an element of order p, what we're looking for is a size 1 orbit where x is not the identity element, because the identity element has order 1, not order p. So let's think about why this is. So the number of these p-tuples, the size of the set is the size of G to the p minus 1, and notice that p divides this because p divides the size of the group. So the size of the group is a multiple of p, so the size of the group to some power is a multiple of p as well. Okay, so note that the identity, or the p-tuple of the identity element is a fixed point. And all the other elements, so g to the all the other p tuples, size of g to the p minus 1 other elements sit in orbits of size 1 or p. But now this number p does not divide that because it's without this thing here is a multiple of p, and if we subtract 1 from it, of course that's not a multiple of p because that's a consecutive number. So what this means is we can't just have orbits of size p and get this number in total because that's not a multiple of p. So thus, and let me just say, thus, because of this, there must be some other size 1 orbit, which is some x comma or x p tuple of x comma up to x, such that x to the p is equal to the identity and x is not equal to the identity because we've already excluded that element. And that's the proof. There's our element of order p. Isn't that neat? Let's make a quick side comment. By Cauchy's theorem, every group of order 6 must have an element A of order 3 and an element B of order 2. These elements must generate the entire group. You see why? Because A generates an index 2 subgroup and B is not in that. So that means that G must have the following partial Cayley graph with this generating set. So we have a 3 cycle here, we have a 2 cycle, and then we have the other coset right here. So this is almost the full Cayley graph. And we can ask, how many ways can we complete this? Well, there are 2 of them. We can either put the remaining 2 blue edges like this, or we can cross them. This is C3 cross C2, which happens to be cyclic, and this is D3. So that's a neat little way to prove that there's 2 groups of order 4. And as an exercise, we write this up here. Classify the groups of order 8 in this manner. And let me just tell you how that would go. So case 1, suppose that there is no element of order 4. That means every element has order 2 or order 1. There you can prove that the group is abelian, and it has to be Z2 cross Z2 cross Z2, or C2 cross C2 cross C2, whatever you prefer. So now let's suppose that there is an element of order 4. That means that we have a subgroup like this. And then what? Well, there's 4 other elements in here. Is there one of order 2? There's an element of order 2 right here, and the quaternions only has this element of order 2. So we can say, well, if there is one element of order 2, let's take that as the other generator. And now there's a coset of the subgroup generated by A right here. And then we can ask, how many ways can we complete these edges? So we can make the blue edges parallel like this, and we get an abelian group. We can make the blue edges cross like this. I don't think there's any other options. I could be wrong, but I think like if you have these things parallel, then you can't have those cross. It would break the regularity property. And so you can classify, there's the groups like this, but then there's something else you can do. Well, something else you can do, what if there is no other element of order 2 other than this one right here? Well, then you have an element of order, so take an element of order 4 that's not in here. So maybe something like that. And now you have another coset, so say this is A and this is B, and now how many ways can you complete this diagram? And somewhere in here, you're going to have to get Q8, and you're going to have to get the cyclic group C8, and you do not get either of those from this diagram. So basically, this is kind of a way of like, try to figure out how many ways can you complete these diagrams. It's a little bit harder, but you should be able to get 5 and only 5 solutions. Although I should say you'll get more than 5, but some of them will end up being isomorphic. So you'll get the same group in multiple ways. It's a fun little exercise, just to show that there's only 5 groups of order 8. Okay, so I mentioned the Sylow theorems in the introduction, and I want to say a little bit more about them before we get into the content of this lecture. And let's recall the definition from way back in chapter 2. A P group is any group whose order is a power of a prime P. A P group that is a subgroup of a group G is called a p-subgroup of G. Here's a notational convention that we will use throughout this lecture and the following two. We will assume that G is a finite group of order p to the n times m. And anytime we write this, we will assume that p does not divide m. In other words, p to the n is the highest power of p that divides the size of the group. Generally, we will pick a prime that divides the size of the group and isolate that like this. We might do this for several different primes. There are 3 Sylow theorems, and loosely speaking, they describe the following about a group's p-subgroups. The first one describes the existence, namely in every group, every finite group, p-subgroups of all possible sizes exist. The second Sylow theorem will say that all maximal p-subgroups have to be conjugate. And then the third Sylow theorem provides strong restrictions on how many p-subgroups a group can have, or in particular, how many maximal p-subgroups a group can have. So all maximal p-subgroups are conjugate. What is the size of that conjugacy class? What's the size of that orbit? This is something that we will answer using group actions. Together, these place strong restrictions on the structure of a group G with a fixed order, especially if we do this analysis for all the primes that divide the size of the group. Here is a picture of all 5 groups of order 12, their subgroup lattices, and the Sylow theorems that we'll do in the next lecture are going to tell us that these p-subgroups come in towers. So I've colored the p-subgroups for p equals 2 blue, and the p-subgroups for p equals 3 red. And the idea is that for every prime, there is a single tower of p-subgroups that are fully saturated, and the tops of the towers are conjugate, and we can say something about the size of this conjugacy class. And that's the Sylow theorems. Bit of a preview. But before we can introduce the Sylow theorems formally, we need to better understand p groups, and in particular, p-subgroups. Recall that a p group is any group of order p to the n. So we've seen a whole bunch of 2 groups, for example. Any group of order 4, 8, 16, etc., even the trivial group, all of these things are 2 groups. Let's start with something that I call the p group lemma, for lack of a better name. And this says, if a p group G acts on a set via this homomorphism, then the number of fixed points of that action is congruent mod p to the size of the set. Now, I don't expect you to look at this and understand what this means or why it's significant, but I think if I show you the right picture, it'll make sense. So here's a sketch of the proof. I won't even write down a proof. I'll let you do it. It's basically a proof by picture. So suppose G has order p to the n. It's a p group, and it's acting on a set S. Then here's what the action graph looks like. And I mean, I'm just putting, I'm only drawing arrows for one generator. It's very possible that there's another generator, and maybe these things are something like this. I don't know. Maybe there's even longer cycles. But the idea is we have the fixed points, and then all of the other orbits have size p to the k. And actually, we don't even need p to the k. We just need the size of the other orbits are a multiple of p. It has to divide the size of g. So let's count the number of these of the set. So what is the size of the set mod p? Well, all of these orbits contribute 0 because their size is multiple of p. So all that's left is just the fixed points. And that's the proof. So if we add up these mod p, we get 0 plus 0 plus 0 plus 0 plus 0 plus however many fixed points. And that's what the lemma says. In the rest of this lecture and the next 2 lectures on the Sylow theorems, we're going to see a number of results that look like this. There are 2 quantities that are equal mod p. And for all of these, if we set up the correct action, one of these can be interpreted as the number of fixed points, and the other one can be interpreted as the size of the set. So looking at this, what looks like a set? So we have a set of cosets of h in G, and maybe there's some action where the fixed points are the cosets that are in the normalizer. So let's actually read what this is. I didn't read this out. So if h is a p-subgroup of G, then the index of h in the normalizer is equivalent to the index of h in G mod p. So it's really hard to look at this and really understand what this is saying. But here's a picture. So we have a whole bunch of cosets. So our set S will consist of the cosets of h in G. So this is going to be like size of S. And then we're going to have some group action, and we're actually going to let h act on these cosets by multiplication, not G, h. And then I claim that the cosets in the normalizer are precisely the fixed points. And that's something that we'll have to show. And once we have that, then the left-hand side is going to be the number of fixed points. And then by the p-group lemma, we know right away that this result has to hold. So let's prove this so-called normalizer lemma. And I should say, this is my own term. There's 2 results about the normalizer that we will prove in this lecture. And so I called them part 1 and part 2. But if you have a better idea, please let me know in the comments. I'm open to improvement. Let S be the set of right cosets of H. Now, if we let G act on this, we know there's one orbit. But we're going to let the subgroup H act on this instead by right multiplication. So we're only allowed to press the buttons from elements in H. And pressing the H button, or the little h button, sends each right coset hx to hx times little h. Let's write down what the fixed points of this action are, because again, the hint here is that this is going to be the size of the set, and actually we know that that's the size of the set because that's how many cosets there are. So all we have to do to prove this is to show that this is the number of fixed points. And then by the p-group lemma, we're done. So we want to show that the number of fixed points is the index of the normalizer. So the index of h in is normalizer. That's all we have to show. So what does it mean to be a fixed point? So hx little h equals hx. So that's what it means for this coset to be a fixed point. Well, it means for all, I should say for all little h and big H. So this is a fixed point. If and only if, what do you think we should do? Move the x over. If and only if h x h x inverse, so big H x h x inverse equals h for all elements little h. And now what? Well, by our boring but useful, it is useful, isn't it? We use it all the time. By our boring but useful coset lemma, That's the same thing as saying that x, h, x inverse is in H for all little h in big H. And what is this saying? This says that x normalizes H. If we conjugate anything in H by x, we stay in H, in big H. So that's the same thing as saying x is in the normalizer of H. So what is that saying? That says that the cosets that are fixed points of this action are precisely the cosets that are in the normalizer. So if we have a partition, here's kind of a picture of this. So if we have this partition, we have G and we have H and we have, these cosets like this, then, some of these are going to be blue and the others are going to be red. These are the left cosets that are not right cosets. And what we just showed is that this coset hx is, or a coset is in the normalizer if and only if it's a fixed point. And that's enough to imply the lemma by the p-group lemma. Here's a schematic picture of why the normalizer lemma part 1 is true. And we could use the p-group lemma, or we could just do it directly the same way that we proved the p-group lemma. So here are all the cosets of H. And if G was acting on them, there would be one orbit. These would all be connected, because we can get from any coset to any other coset. But if we just let H act on them, then we aren't allowed to press as many buttons, and things become fragmented. And so we get fixed points. And how many fixed points do we have? These are precisely the cosets that are in the normalizer, the blue cosets. And what about these? Well, we get, I should say, the entire set of cosets. This is how many we have. And then if we reduce this mod p, well, all of these things, the size of them is a multiple of p, so these all contribute 0, and we're left with just however many fixed points there are mod p. We have one more results on the normalizers of p-subgroups, but before we state it, let me just remind you. So every subgroup is contained in its normalizer, but we say that a subgroup is fully unnormal if it is equal to its normalizer. Remember this? We have G and we have H, and the normalizer is going to be somewhere like this. And if the normalizer is equal to G, it's normal. And if it's strictly between, it's moderately unnormal. And if it's equal to H, then it's fully unnormal. The normalizer lemma part 2, or number 2, says that suppose G is a finite group of order p to the n times m. Remember, p does not divide m. And H is a subgroup of G whose order is a power of p, but strictly less than p to the n. So it's a p subgroup, but not a maximal p subgroup. Then I claim that the normalizer grows. So the normalizer strictly contains H itself. And the index of the normalizer is a multiple of p. So in terms of the subgroup lattice, say this is G, say this is the identity element. So what you have is, remember I drew those p group towers earlier? Maybe this is like p, and somewhere here we have H. So maybe we have something like this. And let me draw this like I did before. So we have the p. We don't know this yet. We haven't proven the Sylow theorems, but this is kind of how you should be thinking about these things. So maybe for different primes, these are the p subgroups. These are the q subgroups, something like this. And maybe there's, who knows, there could even be other primes. You could have a different prime like this. But the basic idea is if we're not at the top of that p group tower, then the normalizer of H, it's going to get bigger. So, I mean, what I mean by this is taking the normalizer is going to be up here. And also, this index has to be a multiple of p. So what can't happen is that we can't go out here and maybe the index of this is something that's not a multiple of p. So now we don't necessarily have to stay in this tower. Maybe this is normal and the index is way up here. Maybe maybe the normalizer is way up here, and so the index is like p cubed, and then some other r up here, something like this. But the idea is that the normalizers always grow unless we're at the top of the tower, in which case it's possible that these things could be their own normalizer. And this is how we're going to prove the Sylow theorem. We're going to start with we're going to start with an element of order, a subgroup of order p, and we're going to show that there are subgroups of successively larger powers of p. But that's not till the next lecture. Here's another unrelated picture that kind of hints at how the proof is going to go, and also maybe some insight as to why this is true. So as before, we will show, so what we're going to do is show that we're going to use the p-group lemma to show that the number of fixed points is equal to the size of the set, and our set, or sorry, size mod p, so that subscript, I mean, that's mod p. So our set, as before, is going to be the set of cosets, and the fixed points are going to be the normalizer. So it's the same idea, but now what are we going to show? So this is a multiple of p, and what that means is this is 0 mod p. So this is going to be 0 mod p, and in particular, if we can show this, if we show one of these is 0 mod p, we know the other one is. That means that this is going to follow right away, because what's the only way that a subgroup can be fully anormal? Well, that happens precisely if the normalizer, or if the index of h in the normalizer is equal to 1. And if we can show that that is 0 mod p, then that completely eliminates this possibility. There are two important corollaries of this lemma that I want to point out. The first one is that p groups cannot have any fully anormal subgroups. In other words, for every subgroup in a p group, the normalizer grows. And if you think about, remember in chapter 2 at the very end, we talked about how pretty much almost all finite groups are p groups, at least asymptotically. Something like 99.2% of the groups of order less than 2000 have order 1024, a power of 2. So even though the Sylow theorems study non-p groups, it's worth mentioning that, and maybe it's surprising, that you don't have any fully anormal subgroups in the vast majority of finite groups. Secondly, in any finite group, the only fully unnormal p subgroups are maximal. So if we have I've already said that, so if we have those p groups in towers, then only the tops of the towers have any chance of being fully unnormal, at least among the p subgroups. Here's one more picture that I want to show you. I don't know if this helps or not. So suppose a subgroup H here is properly contained in a maximal p subgroup. So the order of H is a power of p, and this is contained in a larger p subgroup, and there's cosets of that. Then the normalizer of H must grow in p. So that means that if there's at least one other blue coset inside of p, but the normalizer of p does not have to grow. It turns out it might grow. Maybe the normalizer are like two of these things. Maybe this is normal and the normalizer is everything, but it could also happen that the normalizer of p is p itself, but that's not going to happen for any of its smaller subgroups. Okay, so let's state the normalizer lemma one more time. If we have a p subgroup H that is not maximal, then its normalizer is strictly bigger, and the index of it in its normalizer is a multiple of p. Let me remind you what part 1 says, because we will use that directly. It just says that the index of H in the normalizer, mod p, is the index of H in G. And remember, that's a special case of the so-called p-group lemma. Okay, so how are we going to prove this? Well, since H is normal in its normalizer. That's always the case. That's by construction. This is the largest group, subgroup in which H is normal. We can define the quotient. We can create the quotient. And here, even though I've been preaching that you can always quotient by any subgroup and get a G set, I really mean the quotient group. So actually, let me say the quotient map. So let's call that pi and send the normalizer to the quotient by H. So in other words, that's just going to send an element G to a coset GH, which is equal to HG because H is normal. So remember that anytime that we have N is a subgroup of G, we can always define the canonical quotient that just takes an element and sends it to the coset containing it. Okay, so the size of this group is just the number of cosets. So this is a group of order, or the index of H in the normalizer. Again, this is a group consisting of this many cosets. So now we are going to apply the normalizer lemma part 1 right away. And what can we say? So let's write that down. So by the normalizer, part 1, we know that the size, I'm just going to copy what I've circled down here, and then I'm going to build off of it. The index of H in its normalizer, mod P, is the index of H in G. But let's use Lagrange's theorem. So this is the size of G over the size of H. And again, that's just Lagrange. And now what can we say? This is P to the N times M. That's an assumption. And remember, the size of H is a smaller power of P. So this is P to the I. And so this is P to the N minus I times M. And since I is less than N, this is a multiple of P. So I should say that this is 0 mod P, because again, this is a multiple of P. We're doing everything mod P. So that just means that these two things are both multiples of P. And let me just remind you, I mentioned in the previous slide, but let me remind you that, recall that the only way that the normalizer of H can be equal to H is if the, maybe I should have switched the order of these, but the normalizer of H is equal to H if and only if the index is 1. So once we know that this is 0 mod P, there's no way it can be 1 because 1 mod P is not 0 mod P. So this tells us that, and it also can't be 0 because this has to contain this. So thus P divides the index, and that's what we want to show. And it follows right away that there's no way that these things can be equal. Yeah, so the normalizer must be strictly larger than H. And that's the proof. Okay, now we have all the tools that we need for the Sylow theorems. And we'll do the first 2 of them in the next lecture. And then we'll do the third one in the final lecture of this chapter. At least I think it's the final. Maybe I'll add one later. And the reason why we're splitting them up is because I think the first 2 will take the length of a normal lecture. But also the third one, there's a lot of applications, things we can do with it. In particular, we can use it to prove that a whole bunch of groups are not simple. So statements like, there are no simple groups of order 12. There are no simple groups of order 90. and things like that. And then a few other surprises as well. So we're almost there. Stick around. Don't miss the Sylow theorems. I'll see you next time.